I'm going to give you a little bit of history first, and again, you don't need to start taking notes on this if you don't want to. I'll tell you when we get to the part that IB expects you to know for the current IB curriculum, but I do think this is information that is good for you to have under your belt. And let's go way back. Let's go way back to Aristotle, which is kind of where we like to start usually in these discussions, because he was one of the first guys to try to explain the world around him that we know of, and actually wrote down his thoughts and his explanations. But remember, again, he was a philosopher. He was not a scientist. So a lot of his theories were good, but not necessarily correct. And here's what he said. He said, okay, I take a heavy object, I drop it, it falls. The reason it falls is because it wants to be like the Earth. We talked about this a little bit earlier, right? It's made of Earth. This is made of rubber, but it's made of Earth, and therefore it wants to fall like the Earth. However, if I had something light, like, say, smoke, when I blow out a candle, the smoke rises because it wants to go up to heaven where the air resides, because it's made mostly of air. He said the thing that makes heavy things fall, I'm going to call that gravity. The thing that makes light things rise, I'm going to call that levity. And they have this property of levity and gravity, and that's what makes things go up and down. But naturally, things would like to be at rest. Now, once you got beyond the realm of air here on Earth and you went out into the realm of heaven, where the gods lived, way out there, everything wanted to go in circles. And the reason everything wants to go in circles is because the circle was considered the perfect shape. You got to remember, the Greeks were incredible mathematicians. They believed in mathematics. They discovered a lot of mathematics that we still use today, and especially geometry. They loved geometry. And to them, the circle was the shape of perfection. And it was therefore the shape of the heavens, and everything that went in the heavens was going to go in circles. This was really nice. The stars appeared to go around us. The sun appears to go around us. The moon appears to go around us. Looked really, really like a really good theory. However, there were these 5 weird stars that were called the Wanderers. And they bucked the trend a little bit. They didn't do what everything else did. If you went out and watched the stars year after year after year, you would see Orion every year, and it would look exactly the same, and it would rise in the east and set in the west every winter. And you'd see Leo, and you'd see Canis Major, Canis Minor, all those things. They look the same, but there were these 5 stars that year after year after year would move. They would wander through the night sky, and that was the key to breaking down this whole conception of how the universe worked. So in order to explain how the universe worked, you were going to have to explain the motion of these 5 wanderers. Now this, what's that? You bet, you bet. At this view, this is kind of a picture of the Aristotelian view of the universe. And yes, the Earth is at the center and is stationary. And it's surrounded by these ever-increasingly larger spheres, okay? And notice that you have a sphere for each of these 5 wandering stars. And the Greek word for wanderer, what is the Latin word for wanderer? Planet. And that's what we call them today, is planets, okay? So these 5 wandering stars, or what we call planets, they have their own spheres. And then you go out into the sphere of the stars beyond and the heavens. And that was kind of how the world worked. But why do those 5 wandering stars do this weird thing? Because here's what they would do. Hang on one sec. Let me see if I'll... Come on. I've completely lost control of everything. Okay. Okay. So for those of you that have taken astronomy, you might recognize this a little bit. Here we have the constellation of Orion, Gemini, Taurus, and Cancer, right? Okay. Those are 3 of the constellations in the zodiac, and one that's just an awesome constellation of Orion. And if you see them this winter, this is what they're basically going to look like. If you go out and look at them next winter, that's what they're going to look like. When Aristotle looked at them, that's what they looked like. They looked like that year after year after year. But these 5 wandering stars do something different. If, for example, you saw a bright star-like looking object there last year, when you come out this year, it's probably going to be over here. It will have moved. And it will gradually work its way through the zodiac, pretty much going from west to east the whole time. However, every once in a while, the planets do this weird thing where they double back on themselves, move the other direction for a little while, and then go back to their general path from west to east. That motion is called retrograde motion. And that is a great question, and that is exactly the question that these guys were asking. If you have a model of the universe, it better be able to explain retrograde motion. It's got to, because it happens. We observe it all the time. And so Aristotle's model was pretty nice. Okay, we get back to Aristotle's model. It was pretty nice. But how does it explain retrograde motion? Why do these wandering stars go forward and then sometimes go backwards? Well, he didn't have a great explanation for it. But a little bit after Christ was born, this other guy comes along. His name was Ptolemy. Lived in Alexandria, Egypt. We don't know a whole lot about him, but he did create a model to try to explain the motion of the heavens. And his model was still geocentric. The Earth was at the center of the universe, and everything goes around. And the way he explained retrograde motion is he said all the planets have perfectly circular orbits around the Earth, but around these circles, they do smaller circles, what are called epicycles. And so mathematically, he was able to actually be able to come up with a geometric model that he could map out how the planets moved and did retrograde motion. So Venus, for example, he could say, look, well, Venus is going like this, meow, as it goes around the Earth because of this little epicycle motion relative to its deferent motion, or its larger circular motion. It was a great model. It really made good predictions about where the planets should be and what they're going to do. And it worked really well enough that people pretty much believed it for 1,500 years. If you come up with an idea and people believe it for 1,500 years, it's a pretty good idea. It's doing a good job of explaining how things work. But the Ptolemaic model was not perfect. And, yeah, here you go. Here again is a geocentric model of the oh no, this is not geocentric. This is different. Notice this model looks very similar, but it's different because what's at the middle? The sun. And this was presented to us by Nicholas Copernicus. Nicholas Copernicus was a Polish astronomer. He lived in the late 1400s, early 1500s. And he recognized that you could explain retrograde motion. You could explain the motion of the heavens by, instead of having the Earth at the center, put the sun at the center. Make the planets go around the sun, including the Earth, and you can explain how retrograde motion happens. And let me show you if this website's still working. Yep, nope, it's not still working. But think of it this way. If the Earth, where would we put Earth in here? Here's the Earth. It's right here. And let's say Mars is, we'll make Mars red, is right here. Then Mars is going to appear to be out there in space to us. And the Earth is in a smaller orbit than Mars, so it goes faster. So as the Earth goes by Mars, it will make Mars appear, here's the Earth, to move backwards relative to the stars. But then once we kind of go around the bend and Mars continues on its orbit, it will then continue back through the stars in the same direction. So that's how he explains retrograde motion, by us passing the planets, which it's just it's perception, really. They don't actually stop and go backwards, but when we pass them, they appear to go backwards for a short period of time, and then they start going forwards again through the stars. Okay? Exactly. You're on the highway driving a car. You're going 60 miles an hour. Someone's going 40 miles an hour. You're still both going forward, but when you pass that car, it appears that it goes backwards, right? Same sort of thing with retrograde motion. It was pretty awesome. Now, Copernicus was a pretty smart guy. He knew that this was a dangerous idea because the church was pretty entrenched with the idea that the Earth was the center of the universe. And so he knew that if he said something about this, he'd get in trouble. He wrote a whole book about it, trying to explain his view, but he did not publish it. He did not publish it. When he was on his deathbed, when he was about to die, he said, hey guys, look at this book I wrote. Check it out. And then he died. So they couldn't kill him, right? So it was pretty smart on his part. So he gives the book to somebody. They publish it. They're like, oh, this is great. But it was not, I just want you to recognize that it was not immediately recognized as truth. A lot of people had a hard time believing it because in order for this model to work, in order for the Copernican model to be real, the Earth has to be going around the sun once a year, and the Earth has to be spinning once every 24 hours. Okay? They didn't, and the Earth is flat. We can talk about that argument for a while, but let's get away from that because I don't believe that everyone thought the Earth was flat, because anybody that's ever seen a solar eclipse or a lunar eclipse would see the shadow of the, there's a lot of people that knew the Earth was round, but most people would have an incredibly hard time. Now, you guys accept this because we've been telling you this from the time you were born, and you accept it as reality, but think about your experience for a second. If I came up and told you, what are the stars doing, and you had no experience, and we hadn't been telling you this since you were a kid, and you had to describe what was going on, you would probably say, well, the Earth's kind of just sitting here, and when I watch the sun and the moon and the stars, they're going around the Earth. That model makes sense. We look back on it now, we say, God, that was kind of stupid of them to think that. But if you actually stop and think about it, it makes total sense, because that is what you observe. And if I came to you, if you believed that, and I came to you and said, you know what, no. The Earth's not stationary. The Earth's actually spinning. You're going about 700 miles an hour, spinning around a circle. You would look at me like I was crazy. You were, and this is what a lot of people said with the Copernican model. That's insane. First of all, if the Earth is spinning and I'm moving at 700 miles an hour, one, why isn't there a 700 mile an hour wind blowing past me right now? Huh? How about that? And how about this? Why, if I jump up in the air, don't I go flying off to the side and the Earth spins underneath me at 700 miles an hour? Doesn't happen. See? That's ridiculous. And finally, if the Earth is spinning that fast, why don't I go flying off? If the Earth's spinning that fast, why don't I go shooting off into space? Those are valid arguments, and those were big arguments against the Copernican model. Now, you've already answered number 3. Why don't I go flying off into space? If you think about the intro questions you just did, then it'll start to make some sense, okay? But we'll talk some more about that, okay? So the next character in the story, really interesting guy named Tycho Brahe, okay? Or Tycho Brahe, but I call him Tycho. Some people call him Tycho, potato. This guy was, he was born in the mid-1500s, and he was born into the Danish nobility. What that basically means to you and me is the guy was incredibly wealthy. Okay, he was one of those Red Mountain folks. Big old house, right? Castles and stuff. He could have done nothing with his life and been comfortable and happy, sitting around eating and partying and drinking because he was nobility, okay? But a couple things happened to him. When he was 14 years old, he saw an eclipse. He thought that was really cool. He's like, wow, that's really cool. And so he decided, I want to learn more about this. So at 17, when he was 17 years old, there was supposed to be this conjunction between Jupiter and Saturn. They were supposed to come really close to one another in the sky. He went out to watch it, and it didn't happen. And it's like, that's weird. And he went out the next night to watch it, and it didn't happen. And he went out the next night, and then it did happen. He's like, wow, that's bad. The best astronomers in the world today can't even predict when the two planets are going to be aligned, and they're 2 days off. He thought that was really, really bad. So again, this guy was wealthy. He could have done nothing with his life, but instead he decided he wanted to devote his life to astronomy. So he went to the king, and he said, I want to be an astronomer. And the king said, great, here's an island, and gave him an island off the coast of Denmark. Okay, it's kind of nice. Gave him this little island called Ven, H-V-E-N, and he built the most technologically advanced observatory that had ever been built, okay, ever. But think about this for a second. This was still kind of both things were going on, okay? There were no telescopes. Telescopes did not exist at this time, okay? So he built this really awesome observatory, but they didn't have telescopes. What it had were these really incredible devices to measure angles, really fancy protractors. And they spent years, he spent like 20 years measuring angles. Very, very precisely measuring where these wandering stars, these planets, how they move through the sky and getting the most precise measurements anyone had ever taken. He did this for 20 years, and he tried to unlock the mystery of what they do and how they do it. Tycho made some great discoveries, and you might have learned about this in astronomy. He discovered this new star in Cassiopeia, what we call a nova. It appeared one night. It hadn't been there the night before. Wow, this is cool. We call it Tycho's supernova, and you can actually still see the remnants today with a really powerful telescope. But when this new star appeared in Cassiopeia, it helped kind of disprove that the heavens don't ever change, because that was one of the church's belief, that the heavens were the realm of God, everything moved in perfect circles up there, and everything was perfect and unchanging. Tycho found a new star in Cassiopeia, and that was kind of the beginning of the undoing of that idea. But he was a geocentrist. He still believed that the Earth was the center of the universe, and he collected all this data, and he tried to come up with a model to explain the motion of the stars and planets with the Earth at the center. You don't really need to know his model, but it was a weird one. Here's kind of what it looked like. He had the Earth at the center. This would be the Earth right here. Here's the moon. And the sun going around the Earth, and then all the other planets going around the sun. So he didn't really go against the church. He still said, hey, yeah, the Earth's at the center, no problem. And I'm going to put the sun going around the Earth, but everything else going around the sun, so we're still kind of the best. And it's a real obscure model. We don't really talk about it very much, but that's what he did. Okay. Then comes along this guy we've heard of before, Galileo Galilei. Now's the stuff that you probably need to start thinking about for IB, okay? We know Galileo and his study of motion and how his law of falling objects and all that stuff, but what he did in astronomy is truly remarkable. The telescope was invented about the time that Galileo was famous. And again, I want you to remember that Galileo was a very famous scientist. He was a rock star. He was. I mean, he was a very famous guy. And do you guys know what telescopes were invented for? No. Boats. They were not invented to look out in space. They were invented to look out over the ocean. Because back then, maritime power was the most important thing. If you had a good navy, you were very, very powerful. And this guy that invented the telescope, it gave him an advantage. It gave their country an advantage because you could look out and see if there's ships on the horizon. You could see if they were enemy or if they were friendly much earlier than you could without a telescope. An earlier warning was helpful. Galileo took the telescope and he said, well, this is pretty cool, but what if I pointed it up to the heavens? I wonder what I would see. And he saw some amazing things. Do you guys remember what he saw, some of the things?
Stars.
He did see some stars. And they still looked like little points of light, so that was weird. He studied sunspots, he studied the moon, he studied the planets. And what did he see most specifically that was the most important thing in terms of the planets? Okay, we'll go through it here. Okay, so he didn't, and a lot of people think Galileo invented the telescope. That's not true. Okay, and by the way, this is about, what's that? He improved on it, exactly. He was a very good technician, and he did make them better, but he did not invent it. And it's been about 400 years since he took his telescope and aimed it to the to the heavens. He did see sunspots. Okay, actually, he went temporarily blind for a little while with his observations of the sun, but sunspots. This was important because the sun was not perfect. It wasn't this. It's a cooler region of the sun created by a magnetic disturbance, which not totally important. But what's important here is that the sun was not perfect. Here's an object up in heaven. It's not perfect. You guys have been telling us the things in heaven are perfect. The sun's not perfect. Okay. And then he goes and he looks at the moon. And look, the moon's not perfect either. There's mountains on the moon. And not only did he see mountains on the moon, this guy was so amazing. He actually measured the height of these mountains using the angles of the shadows that he observed and geometry to measure how tall those mountains were. And I want you to recognize, too, that his telescope was about as powerful as a decent pair of binoculars today. It was nothing like the telescopes we have today. It was like binoculars. So take a pair of binoculars and look at the moon and think about, could I measure how high those mountains are by doing geometry? And that's what Galileo was doing, okay? Totally crazy. This was critical. This was critical. He looked at Jupiter, and he discovered 4 moons orbiting Jupiter. We call them the Galilean moons today: Io, Europa, Callisto, and Ganymede. They're the 4 largest moons of Jupiter. Yes, you can see them with a pair of binoculars. If you've never seen them, take out some binoculars, look at Jupiter tonight, and hold real still, and you'll see at least 2 or 3 of them, and sometimes you'll see 4 of them. They look like little stars, perfectly aligned along the equator of Jupiter. It's pretty darn cool. He discovered these things. He mapped them out for a long time and measured their orbits. This was huge because it was the first definitive piece of evidence that the Earth was not necessarily the center of the universe, that there were other objects going around other things in space. That was big because it was like, all right, here's a piece of evidence that the Earth is maybe not the center of the universe. He also noted that Venus went through phases. He saw the planets got brighter and dimmer, and all of this helped to kill the geocentric model and helped to support the model where the sun is the center of the universe. Again, he was powerful. He was arrogant. He wrote a book about this, and he made the Pope look really stupid. The Pope did not like that. They took him down into the dungeon and said, Mr. Galileo, we've been reading your book here, and we don't like this. We have these machines over here. They cause excruciating pain when used on people. We would like to use them on you unless you sign this paper that says everything you have written is incorrect. And Galileo looked at the torture devices, and he said, I'll sign that piece of paper, thank you very much. And he signed the piece of paper saying that what he had written was wrong. And then they said, you know what, for the rest of your life, you will be under house arrest. You may not leave your your home. Now, his home was pretty nice. I mean, it's not that big, but still, he ended his life under house arrest, and because of his discoveries and the fact that he went straight against the church right in their face, which was not a great idea. Okay. Then along comes this guy named Johannes Kepler. Johannes Kepler. Johannes Kepler was a German mathematician. Okay. He had an incredibly tough life. Okay. He had an incredibly tough life. Just to give you a little bit of an idea about Johannes's life, his aunt was burned at the stake for being a witch. His mother was considered to be a witch. He never really knew his father. He was raised by the church because his mother couldn't raise him. Over the course of his life, he had 2 wives, 11 children. 7 of his children died, and they were not witches. So he had a hard life, but he was brilliant. This guy was a brilliant mathematician. And he got a job working with Tycho Brahe. Remember, Tycho was the guy that had this observatory and these notes. Now, here's the weird thing. This is kind of weird. We'll talk about this. I'm going to back up for a second because I don't want you to see that yet. But he worked with Tycho for years and years and years, and he wanted Tycho's data. He wanted to get this information that Tycho had been measuring for years. But Tycho knew that Kepler was brilliant, and he didn't want Kepler to make him look bad. So he would give Kepler a little bit of information. He'd say, Kepler, because Kepler was the assistant, he'd say, Kepler, here's some data on the moon. Go play with this for a while. And Kepler would be like, and he'd go and he'd play with it, and he'd learn some stuff about the moon. And then he'd go, oh, here's a little bit more, and go do something with it. And he would never give him all of his data. And Kepler's just like, give me your data because I can figure this out. I can figure out how the universe works. Anyway, he didn't do it. But Tycho Brahe did a bad thing. He was at a party one night. And this was a big party. The king was there, I think. There was a bunch of royalty there, and they were having lots of wine and food and stuff. And he was the host. He was at the table. He was at the host. He'd been drinking wine. He needed to go. Yeah, no, he needed to go to the bathroom, and he didn't do it. He didn't do it because he was the host. He didn't want to leave the table. That would have been rude. And so he held it and held it and held it as long as he possibly could. They had a great party, but he never went to the bathroom. It ended up that he ended up getting some sort of a weird bladder infection. I don't know if he actually ruptured his bladder or not, but he ended up dying because of this. Okay, he ended up dying because of this, and it was a painful death and a slow death. And while he's there on his deathbed, there's a couple different stories, and some of this sounds a little bit like Days of Our Lives, and I don't know what's the truth, but when he's on his deathbed, he's got all this data, 20 years of data he's collected, and he finally is dying there, and he says, Kepler, I do not want to have lived my life in vain. Take my data and do something great with it. And Kepler's like, oh, right on. And then the story goes, I don't know exactly what happened, but somehow either like Brahe's family didn't want Kepler to have it, so they took it back and said, no, you can't have it. And Kepler's like, ah. And then Kepler goes in the night and like breaks it in the house and steals the stuff and runs away with it. Something happened, but it was really ugly. Eventually, Kepler got the data, and he set to work to try to figure out how the universe works, using the best data that anyone had ever collected. And he was brilliant, but he was on the wrong trail. Here's what he thought, and this was kind of cool. There was 5 planets at that time, 5 that we can observe without a telescope. This is Galileo-ish similar time, kind of some overlap going on here. And he said there's 5 planets, but you know what? There's 5 perfect solids, according to the Greek mathematicians. And talk to your math teachers about what that means, because I'm not sure exactly, but it has to do with like a geometric solid that I think all the sides are equal, something like that. And there's 5 of them. So he said if there's 5 perfect solids and there's 5 planets, this could not be coincidence. There must be connection. And he set out to explain a model of the universe of how the planets move by trying to explain it geometrically with these Greek solids, these geometric shapes, and never was able to do it. He had another theory that was really awesome, too. He was really into music being very mathematical in nature, particularly classical music. And he thought, you know, there's got to be a connection between music and what is harmonious to us as humans and how the planets move. And he looked into that relationship for a long time, too. Never found anything. But he looked specifically into the orbit of Mars very, very carefully, and he did discover 3 things, and they're known as Kepler's 3 laws of planetary motion. And yes, that's what you've seen before, okay? Here are his 3 laws of planetary motion. 1, the planets do not move in circles. Up until this point, everyone thought the planets moved in circles, okay? Copernicus's model of the universe was incorrect. Yes, he put the sun at the middle of the solar system, and that's great, but he said the planets moved around the sun in perfectly circular orbits. And no, Kepler said, no, actually it's elliptical. 2, the equal area law. Planets sweep out equal areas in equal time. And then 3 is the one that's actually mathematical. And he discovered that there was a mathematical relationship between the period of a planet and its radius. The period of a planet and its radius. That's what the third one means. So let me show you this a little bit differently. Wait. So what the heck does this mean? Let's take a look. Oh, I hate it when that happens. Okay. So this is an ellipse. That's a very poorly drawn ellipse. But the idea of an ellipse is it's more of an oval shape than a circular shape. That's his first law. The planets don't move in circles, they move in ellipses. His second law was the equal area law, and it meant this. If you guys have studied ellipses in math, you know that a circle has a center, an ellipse has 2 center-ish things that we call foci. And the sun exists at one of the foci, and then there's another one out here in space. And what he said is if a planet's going around the sun, okay, and I pick a time period, let's say this is 2 weeks, and I measure this area that the planet sweeps out over the 2 weeks, it will sweep out the same area no matter where it is in its orbit every 2 weeks, okay? So out here, if I picked a 2-week period and I measured this area, it would also be equal.
Is that correct?
And it is correct. And here's another one, and if that was true, it would be the same. He did not know why. This is what's known as an empirical theory. He had data. He knew his data provided him with this idea, but he did not know why it worked. He just knew that it did work. This is called the equal area law, okay? And what does the planet have to do in order to make this happen? Look what's going on. It has to move in an ellipse, but what has to happen with the planets? What? Not quite. Slow down and speed up. And when does it have to be going faster? Okay, so here it's going faster, and out here it's going more slowly. That's basically what the second law is saying. It sweeps out equal areas, and in order to do that, it has to be moving faster when it's closer and slower when it's farther away. That's the equal area law. His third law, which is the mathematical one, can be written a variety of ways, and I'll show you kind of what that means. Okay, t squared of A over t squared of planet B is equal to r cubed of planet A over r cubed of planet B. If you take 2 planets, or any planet, if you take a planet and take its period squared and divide it by its radius cubed, you'll get a number, you'll get a constant. And that constant is the same for all planets orbiting the sun. This actually works for moons orbiting a planet as well. I could use this law for the moons of Jupiter, for example. If I take the period of 1 squared divided by its radius of its orbit cubed, I'll get a number, and that number will be constant for all of the moons of Jupiter. He didn't know why, but it worked. So here's you can compare 2 different objects, their periods and their radii. You could also rearrange this equation to say t squared over r cubed of planet A is equal to t squared over r cubed of planet B. You can look at it that way. Or you could just say, hey, t squared of a planet over its radius cubed is constant for any planet that's orbiting the same object. That's all Kepler's third law. It allows us to do things in terms of discovering radii and periods. If you find a planet and you know how far away it is from the sun, you can calculate how long it's going to take to go around the sun. That's what Kepler's third law allows you to do. So there's Kepler. Oh, well, let's see if this works. Probably it's not going to, but we'll try it out anyway. So here's a look at Kepler's second law, again, the equal area law. A planet or anything that is in orbit, it's got an elliptical orbit, and it'll always sweep out equal areas in equal times. And essentially, again, what that means to you and me is that when a planet is closer to the sun, it must move more rapidly. When it's farther away, it must move more slowly. Kepler didn't know why this worked. He just knew that it did work, and it was pretty darn cool discovery. Newton will kind of explain why it works. So here comes Isaac Newton after all this other turmoil. The whole heavens are being totally reshaped and rediscovered. We're putting the sun at the center of the universe instead of the earth at the center of the universe, and everything's changing. But the cool thing that Galileo did is he started to ask why, not Galileo, Newton, is why the heavens moved the way they moved, okay? And the story goes, you've heard the story of Newton and the apple probably. He's out there in the orchard and the apple falls, and he starts thinking about it. But here's what he did that no one had ever done before him. He saw an apple fall, and he said, hey, gravity's making that apple fall. That's pretty cool. And he looked up, and he saw the moon. Why would he assume that the moon is accelerating? Because it's moving in a circle. It's moving in a circle. So it's accelerating. So there must be a force acting on the moon. And he said, I wonder what that force is. I wonder if the force pulling on the moon is the same force that pulled the apple down from the tree. No one had ever thought that before. No one had ever considered that the forces and the things that happen on earth are the same as the forces and things happening in heaven. Because heaven was separate. Heaven was realm of God. Heaven was perfect. Earth was not. No one had ever made that connection before, and Newton did. And not only did he make it in a thought way, but he also made it in a mathematical way. He set out to prove that the force pulling on the moon was the same force pulling on the apple. And he did it, and you could do it if you wanted to, because you have the tools. Here's what he thought. He said, I know the apple falls at 9.8 meters per second squared. And, well, hold on, I'm getting ahead of myself, because he couldn't think that yet, because he hadn't come up with his law yet. But he's with these concepts, and a lot of thinking, took him about 20 years. Okay, remember his 3 laws of motion he did by the age of 23? His universal gravitation law took him a long time. And actually, I've read somewhere that he actually came up with his law of universal gravitation and then kind of forgot about it and left it somewhere, like didn't even worry about it because it wasn't that big of a deal. And then years later, a friend of his, like Edmund Halley or someone like that, came up to him and said, what did Edmund Halley? Yeah. And said, hey, stop, you guys. I'm trying to figure out something about this comet. I need to know something about gravity and whatever. And Newton's like, oh, I think I did something about that a long time ago. And he went and got it, and went back and looked at his papers and tried to rediscover this thing that he had discovered before. But here's what he did. He said, you know what? First of all, okay, if gravity is keeping the moon in orbit, and it's the Earth that's pulling on the moon, and the moon's pulling on the Earth, well, I bet you that force of gravity, because, you know, I came up with these 3 laws of motion. My third law of motion, what does my third law of motion say?
Opposite.
Equal and opposite what? Forces. So if the Earth's pulling on the moon's probably pulling on the Earth. So gravity probably has something to do with 2 objects pulling on one another. So that's going to be part of my theory. Cool. And he said also that I suspect that gravity will get weaker with the distance squared. If I double the distance between 2 objects, I bet you the force is 1/4 as large, simply because the surface area of a sphere increases with the square of the distance. So there's a relationship there. But I want to prove it. And they knew that the moon was 60 times farther away from the center of the Earth than the surface of the Earth was. That the moon was 60 Earth radii away. The Greeks had measured that a long time ago. They were good at geometry, okay?
That doesn't explain it.
Oh, yeah. No, it does. Okay. So he calculated the acceleration of the moon. He knew how long it took the moon to go around. He knew the radius of the moon's orbit. And he calculated that the acceleration of the moon was 1/3600th of 9.8 meters per second squared. That the moon was accelerating at 1/3600th that rate towards the Earth. He knew that the moon was 60 times farther away from the center of the Earth than the apple was that fell on the ground. And so he looked at that, wow, 60 times 3,600. So yes, there must be some relationship with distance squared. He considered his third law of motion, that, you know, for every action, there's an equal and opposite reaction. So gravity, if the Earth's pulling on the moon must be pulling on the Earth. And he came up with an equation to describe gravity. And by using the moon, he was able to prove that this equation should work. And here's what his equation looks like. It's the law of universal gravitation. You want to go back? Write this down. Now think about this for a second. This is pretty amazing stuff. So here's his law of universal gravitation. This is an equation that is extraordinary and is extraordinarily powerful. It allows you to calculate how much gravitational force exists between any 2 masses in the universe if you know their masses and how far apart they are. M stands for mass A and mass B. Here I have in the denominator d squared. Occasionally you'll see this written with an r instead of a d. And what that is the distance between the center of mass of the two objects, squared. What's that? No, d is distance, r is just radius. Yeah, no, d is distance in this case. And then there's this big G. The big G is a constant, okay? It's the universal gravitational constant is what it's called. And in the time of Newton, they didn't really know the value of that constant. It's a hard thing to measure. How are you going to measure the strength of gravity, okay? D is the distance between the centers of the masses, and G is constant. Now think about this for a second. Now we have a mathematical equation that allows us to calculate the force of gravity between any two objects in the universe. We know that the force is proportional to the masses, or the product of the masses, and inversely proportional to the square of the distance. This is profound. This is profound, and it should affect your life dramatically. Think about this for a minute. You wake up in the morning, and you're like groggy, and you're tired, and you're grumpy, right? And you go, and you're in the bathroom, and you're looking at, you're brushing your teeth, and you're looking in the mirror, and you're like, God, man, I'm just pathetic. I don't know if I can do it. I don't know if I can go to school today because nobody loves me, right? Everybody hates me. I might as well go eat worms. But you remember Newton's law of universal gravitation. And Newton's law of universal gravitation says that everyone in the universe is attracted to you. Everyone. Right now, there's an attractive force between every single one of you. That's big. That's huge. Okay? All right? And contrary to popular belief in America, the larger your mass, the larger your attraction. Okay? So eat more donuts and you become more attractive. It's pretty darn awesome. Okay? It's a good thing. It's a good thing. So let's see if we can explain this a little bit. All right. F equals GMM over R squared. So here we have, for example, the mass of the Earth, the mass of the Moon. There's a gravitational attraction between them. We can now calculate how big that is. If I were to double the mass of the Moon, what would happen to the force between the Earth and the Moon? It would, in fact, double. What if I doubled the mass of the Earth and kept the Moon the same size? What would happen to the force? It would still double. What if I doubled the mass of the Earth and the mass of the Moon? What would happen to the force? And is that because you added the masses? You multiplied 2 times 2. Not 2 plus 2, but 2 times 2. Because remember, it's F equals GMM over R squared. Now, here's the same thing. We got the Earth, we got the Moon, and we got a certain distance between them and a certain force. What if I doubled the distance between the Earth and the Moon? What would happen to the gravitational force? Why 1/4? Because it's the distance squared, you guys. It's the distance squared. It's inversely proportional to the distance squared. What if I made the distance 1/2 as large? You'd get 4 times as much because it's squared. Remember, it's squared. What if I tripled the distance? What happened to the force? 1/9. 1/9, because 3 squares is 9. Okay? All right. Excellent. Okay? Now, universal gravitation explains the law of falling bodies. It explains Galileo's discovery that all objects fall with the same acceleration, because what is it that causes something to fall? Gravity. So let's look at that for a second, and let's see here. See if I can explain this to you. So an object falls because of gravity between what and what? Gravity between what? I drop the Earth and the object, right? Okay, so the force of gravity between an object is equal to the mass of the object times the mass of the Earth times big G, all over the radius of the Earth squared. So there's another example where R can stand for radius, because the radius of the Earth would be the same thing as the distance to the center of the Earth, right? That's the force of gravity on an object. And Newton's second law says that F equals the mass of the object times its acceleration, right? You with me, Kyle? Yeah? You with me? No, you're not. You're with him. Talk over here. Okay, hey, stop. Hey, be quiet. Just watch. Okay. So the gravitational force between an object and the Earth is equal to the mass of that object times its acceleration. F equals ma. Well, notice the mass of the object is irrelevant. The acceleration of all objects is equal to the mass of the Earth times the universal gravitational constant divided by the radius of the Earth squared. And those three things will be constant for all things. So all objects in the absence of air resistance will fall at the same rate of acceleration. On any planet, it'll have a different rate, but everything will have a consistent rate because the mass of the object is irrelevant. Okay? Okay. Okay, bear with me. I know this has been a long one. We're getting close. Now, so Galileo's law of universal, or Newton's law of universal gravitation did a lot for us, but we still didn't know the value of big G, the universal gravitational constant. We didn't know what that was until this guy came along and did an excellent experiment. His name was Henry Cavendish, and he was the first one to actually measure big G. Now, every once in a while in physics, there is an experiment that is just classic. Like, wow, that was really incredible. And so we need to know about those. We need to be aware of those. And this was one of them. Henry Cavendish measuring the gravitational constant. First of all, because you can't stop gravity. You can't like stop it and say, I'm going to go measure this for a second. I just like have a little piece of it. So how do you measure something that's everywhere if you want to measure the force between two objects? You know, it's kind of weird. So here's how he did it. This is the Cavendish experiment, and it's classic. People still use this technique for a variety of ways. He had a cable that he could twist torsionally, and he knew how much force it would take if it twisted a certain amount. From that cable, he hung a bar with two small masses on the end, and he had two larger masses that he would then bring close to it. And he would see how much the cable would twist because of the gravitational attraction between these two masses, and he would measure that force, and by measuring that force and knowing the masses and knowing the distance, he could solve for big G and figure it out. What's that? Pretty big deal, yeah. That's a good question. There it is. So it wasn't until 1798, it was almost the 1800s when Cavendish measured big G, and here's what it is. We call it big G, the universal gravitational constant, and it has a value of 6.67 times 10 to the negative 11th. 6.67 times 10 to the negative 11th. Now, when you measure mass in, what do we measure mass in? Kilograms. When you measure mass in kilograms and you measure distance in meters, using this constant will tell you how much gravity exists between those objects in newtons. Okay? Now, is 6.67 times 10 to the negative 11th a big number or a small number? It is a very, very small number. What does that tell you about the force of gravity? It is very weak. It is the weakest of the forces by far. It is so weak that I can overpower it easily, right? See that? The entire Earth is pulling on my cup, and I say the Earth is a wimp because I can beat it. Okay, it is weak. It's a very weak force. We don't think it's weak because the entire Earth is pulling on us and we observe it, but it really is a weak force. Okay? And by doing this, yes, Nick.
Okay, it's kind of hypothetical, but it's everybody.
And when Cavendish measured big G, he essentially weighed the Earth. This was the first time we were able to actually find the mass of the Earth, because you can't take the Earth and stick it on a bathroom scale, right? You just can't do that. So how do you do it? Well, if you know some things about gravity, like this, check it out. Okay, we know the force of gravity equals mass times acceleration, and we know that that equals gmm over r squared. So any object that's falling is has a force mass times acceleration. It has gravity. Well, remember, the mass of the object is irrelevant. We talked about that earlier. So the acceleration of an object, 9.8 meters per second squared, is equal to big G times the mass of the Earth over the radius of the Earth squared. We knew the radius of the Earth. The Greeks measured it. But we didn't know the mass of the Earth until we could measure big G. And when we did, he did, and they did, and voila, we knew the mass of the Earth. Okay? It's great stuff. And you can now calculate it if you wanted to, but we're going to move on and do some practice. Okay? Try this out, you guys. Let's see if we can find the gravitational force of attraction between the sun and the Earth. Let's just see how much force there exists between the sun and the Earth gravitationally. See what you get. Well, it's look at that. I mean, it's almost 8. Let's see, 10 to the 21st. That's like 8,000 billion pounds of force between the sun and the moon. I mean, the sun and the Earth. Should it be really small because it's really far away? Well, yes, but what makes it so large? Mass of the sun. The sun's mass is immense. It is so more massive than you can imagine that it's hard to imagine. You know what I mean? It's big. Okay.
Wait, Mark,
What?
have we found
No, because they couldn't really. The planets were just points of light, and the sun. I don't know. I mean, they might have tried.